It's my deep pleasure to introduce our speaker today, Dr. Jeff Monroe. Jeff is a Philip B. Stewart and Sarah F. Cowell Stewart Professor of Geology at Middlebury College in Vermont. Among many cool things, Jeff studies environmental change in the Rocky Mountains and Great Basin of the southwestern US and impacts of mineral dust deposition in mountain landscapes. He's also PI in the dust-squared critical zone thematic cluster, a project he's probably going to talk a bit about today. We're really pleased to have Jeff here, and I will stop sharing so he can take over.
All right, thanks, Jenny. Set that up. All right, it says I'm screen sharing. Can you see my screen? All looks good. Yes, okay, super. Thanks so much. Thank you, Jenny and Karine, Ling. This is just, I really appreciate the opportunity to present to Dana. This is just really an honor. And it's a remarkable situation to come and talk about dust research with an audience full of dust researchers. It's really great. And I see some people in the gallery here that I have known for a long time, and it's really fun that they're here this afternoon. So as the title indicates, just moving some things around, there we go. As the title indicates, I'm going to give you all a little overview of the dust-squared critical zone thematic cluster. And then I'm going to dive a bit deeper into my component of that research, which is focused specifically on dust and mountain soils. Happy to take questions along the way if you have them. I've tried to open as much of the gallery as possible here on my Zoom screen. So if you raise your Zoom hand or you turn on your camera and wave frantically at me, perhaps I would see that. But at the same point, if you want to save them toward the end, my goal is to reserve time for the Q&A. So let's get after it then. I don't know about you, but I have a really hard time giving a talk about dust without starting out with an animation like this one, simply because it does such a nice job of illustrating the staggering amounts of dust that are in the atmosphere at any given time. And in this animation, which is familiar, I'm sure, to many of you, the dust is the orange-brown color, primarily concentrated in toward the center. So there's lots of this material, and the erosion of mineral dust off of the ground surface in arid landscapes, transport through the shallow atmosphere and redeposition on the ground is clearly a really important chain of processes operating in Earth's near surface environment. In the last 20 years or so, the Earth's near surface environment has been frequently abbreviated in this shorthand of the critical zone, the critical part of the Earth, if you will, where the atmosphere and the biosphere, hydrosphere, soils, geology, et cetera, are all in closest contact with one another. And it's also, of course, the part of the planet that we inhabit, so it's critical for us as well. This is a really good model, and it's spawned an entirely new interdisciplinary line of thinking, which has been quite productive. But this diagram, which so often accompanies any introduction to the critical zone concept, gives us the unintended impression that the critical zone is this closed system, and it's just this local spot in the landscape where things are happening, and it's detached from other spots in the landscape. And we think like that quite a bit. Like, we think about that when we talk about mountains as islands in the sky, right? This idea that, you know, a lofty summit towering above the surrounding lowlands is somehow separate or detached from everything else that's happening. And that's not true, right? So it's not true at all. We think about the precipitation that falls in the mountains is going to turn into runoff, which is going to then feed surface water systems and groundwater aquifers at lower elevations. And I would argue things go the other direction too. And this picture here shows what I mean. The islands in the sky are receiving dust, which is blowing up off of the arid landscapes, which often are surrounding them. So this idea of mountain systems as being the recipients of dust and a mechanism that links together the critical zone in different places was really on my mind, particularly back in 2019 when the National Science Foundation released their call for what they were calling the Critical Zone Collaborative Network. Many of you probably read this. Some of you probably were involved in this. In part, what NSF was looking for was a way to move beyond the rather restricted spatial footprints of the well-established and quite successful critical zone observatory model, which had been in operation for more than a decade. And they were proposing that new projects should link together series of potentially widely scattered sites on the landscape that are connected by a common theme. And my idea very quickly was, well, we could probably use dust as a great example of a theme that connects together potentially widely scattered locations within the critical zone. And so I pulled together a team of colleagues to pursue this, and we proposed a project which became known as Dust Squared. Dust across the Desert-Urban-Summit Transect was our clever acronym here. It was designed to explore the role of dust as a theme connecting the critical zone. It was designed to incorporate dynamic forcings on the dust cycle from source to sink. So things happening in the source regions, as well as things happening in the dust receiving regions, and then feedbacks back in the other direction. And I think very importantly, this constellation of projects that comprises Dust Squared was designed to consider a real wide range of both spatial and temporal scales. So on the time end of things, individual dust storm and deposition events that might occur in a single afternoon would be of interest. And at the other end of the spectrum, dust deposition over long stretches of time, 100,000 years or more, and what that does to soil formation. And similarly, the spatial scales from really, really focused what's going to happen in this one study plot, or what will happen to this one snowbank because it has snow on the surface of it, through to the kind of more local or slightly larger local scale with the great natural experiment in northern Utah now, with the shrinking of the Great Salt Lake and the expansion of the Salt Lake Desert and what that's doing as a dust source, what that's doing to immediately downwind areas, and at the widest spatial scales, considering what's going on in the southwestern US in general as an example of a source to sink dust system. I'm certainly not doing this all by myself, far from it. Very quickly, I just want to mention the other PIs on this project and the critical roles that they're playing. Kevin Perry at the University of Utah is the expert on our team who's studying the properties of dust emitting landscapes, particularly focusing on the expanding desert around the Great Salt Lake. Maura Honnenberger at Salt Lake Community College is working with a number of other modeling experts to study the conditions that are involved in transporting dust from source regions to deposition. Greg Carling at Brigham Young University in Provo, Utah is working a lot on dust geochemistry and the effects of dust on stream water chemistry, particularly during the spring snowmelt pulse. Mackenzie Skiles, also at the University of Utah, is working primarily on dust on snow and modeling the effects on advancement of the spring hydrograph in response to the dust content of the snowpack. Janice Brainey at Utah State University is studying specifically the role of the bioavailability of dust-derived nutrients or dust-delivered nutrients and what that's doing for surface water systems in the mountains. And then you finally get to me at the far end of this chain, where I'm particularly interested in the effects of dust deposition over longer term timescales on soil development. So we'll pivot into this idea of diving into dust and mountain soils. It's funny in a way because I could say that, this for me started with the Dust Squared project in 2020, or I could say, as I will explain in a moment, that this might have started for me more than 10 years ago when I began to research dust more directly, but I could actually walk it farther back and make myself feel pretty old because when I was a graduate student and I spent a summer working for the US Forest Service in the Uinta Mountains in northern Utah, here's me in 1996, the Forest Service soil scientists were particularly interested at that time in what dust deposition might be doing to the mountain soils in this part of the Rockies, and in particular, would dust deposition or could deposition of dust over time explain like the high clay content and some of the other things that they thought were peculiar about these soils. So if I'm honest and I take the long view, it is kind of fun to realize that dust and mountain soils is something that I've at least thought about in some way for as long as I've been really doing our science. which goes back a ways. So the Uinta Mountains is where I'm going to start with this. And those who know me know that I've spent a lot of time working there on a variety of projects. We're in northeastern Utah. Here's the Great Salt Lake. Here's the boundaries of the state of Utah. And the Uintas have a really interesting geomorphology, which in part makes them particularly appropriate for these types of studies. They were really intensively glaciated during the Pleistocene. There's no glaciers there now, but this is a reconstruction that I and a colleague made showing in light blue the dimensions of all of the glaciers in the Uintas back in the day, say 20,000 years ago. And the whole landscape was nearly covered by ice, and it looks like it. It looks like a textbook example of alpine glacial geomorphology. But at the same point, if you go back to that figure and look really closely at it, there are areas that kind of run like a catwalk or something between those glaciers. These are high elevation ridges, which were apparently above the reach of that erosive glacial ice. And they're a really, really different landscape. They're gently sloping to flat. They're covered with really well-developed paraglacial pattern ground. And importantly, for the topic of dust, they were not apparently refreshed or reset by glaciers repeatedly during the Pleistocene. They could be very, very old landscapes that have been perched there up high, receiving dust for a long time, much longer than the ages of the landforms and the surficial materials down in the cirque there around that lake and so on, where there clearly was glacial activity not that long ago. So if you dig a soil pit up on this landscape, you invariably find a situation like this, where the lower part of the soil profile is clearly derived from weathering of the underlying bedrock. So it's regolith, right? In this case, it's stony, sandy, pink sediment coming from the underlying bedrock. And that's overlain by material which the Forest Service and other researchers long ago concluded, without a lot of direct study, was most likely an alpine loess deposit. So the dust, which is accumulated over some amount of time, forming a completely discrete layer at the surface of the soil profile. This means that these soils inherently are what they are because of dust deposition. Dust itself is one of the parent materials for these soils, are not solely controlled by the underlying bedrock. These soils are in the Uintas surprisingly fertile, given that the underlying bedrock is primarily a quartzite, which is not going to weather very fast and is not going to release much in terms of plant available nutrients when it does. And yet there's these beautiful blooms of alpine wildflowers on this surprisingly fertile soil. There's a robust ecosystem of animals which are, feeding on those flowers and so on. And so for a long time, I've thought this is just fascinating from a geoecology perspective. What role does dust deposition, this background process, play in essentially controlling the whole geoecology of the way these mountains are functioning? And so in 2011, I wrote a proposal to test the hypothesis that dust was playing a really important role in the form and functioning of the alpine soils in this area. And to go at this, I needed to collect modern dust. And so I designed these dust collectors based off of well-established, tried and true passive marble-based dust collectors, which have been used by many folks in this audience for working at lower elevations. Tweaked them in a variety of ways I thought would make them more appropriate for use way up high in the mountains where there's lots of precipitation. They've worked really well over the years. And as an aside, I did publish the full designs for building all of these in an open access paper last year. So if anyone wants to see what's involved in these or try to make them, I wanted to make sure that people would have that opportunity. But I put the first 4 of these out in 2011. And then when I got funding to expand things, I put 4 more of them out in 2015, scattered around the Uintas. There's the triangles to show you, trying to be north, south, east, west, all of them up above tree lines, so really high elevation locations. The Forest Service required I put them in places where no one would find them, which was kind of an interesting permission requirement, but I was willing to do it. So they're way up high, far from trails. I've never seen any indication that anyone's ever stumbled across one of them. And it's kind of neat. They just sit up there, perched up on top in these lonely, wind blasted, snow covered places. And then I go back to them twice a year to empty the dust out of them, which is a simple process that you can speed up dramatically with time lapse. Scrape out the beads, rinse them off with distilled water, rinse out the collector, put it all back together and bring the water back to the lab. So I try to do this every year in late June or early July to remove what I call the winter dust sample. And then I'll go back in October and get what I call the summer dust sample. So it's not perfectly split 6 months and 6 months, and it's certainly not perfectly split on top of those seasons. But it all has to do with when you can actually access these locations. And the summer one is about when is the snow melting out enough to actually get there? And the winter one is how late do I dare wait before the collector might be covered? And just to be completely honest, sometimes I mess it up and I wait a little bit too long, and then just simply finding the collector is an interesting challenge. But the design and the basic structure of that as a project over more than a decade now has worked, I think, remarkably well. And I wanted to show you some of the data that come from this network, focusing for now just on the 8 collectors in the Uintas. They have revealed really clearly the great degree of variability in dust flux in terms of space and time. So here we're just looking at years across the bottom, and dust flux in grams per meter squared per year. The first 4 years, there were only 4 collectors, and then it gets busier. But you can see clearly not every year is the same, and not every location is the same. And on the one hand, this is not a radical conclusion. On the other hand, it's really nice to have these data from a fairly focused array of collectors in a relatively small area to see just how the time and space components vary. In this case, centering around a mean of about 3 grams per meter squared per year, which matches reasonably well with what little we know about dust deposition rates in similar locations elsewhere in the Rockies. The mineralogy of the material in the dust collectors is very, very similar to the mineralogy of the soil surface and subsurface horizons, and is very, very different, I suppose, than the underlying bedrock. So these are X-ray diffractograms showing essentially the characteristic peaks of various minerals, which I've labeled for you here. This is an important bit of evidence that the soil is really strongly controlled by dust deposition. If the soil in this location were really strongly controlled by weathering of the bedrock, we wouldn't see all of these other minerals in the soil, which are not found in the bedrock. Again, a really simple and perhaps predictable conclusion, but one that without these types of data, you really can't test that idea. The mineralogy of the soil makes it pretty clear, though. And that's nicely backed up by looking at the chemistry of the soil. So in all of these plots, we're looking at a major element or a particularly abundant element normalized to iron in the dusts, in the soil A and B horizons, and in the rock. And what I'm really trying to show you here is that in nearly all cases, the dust and the rock represent end members, essentially, where a particular element might have a really elevated ratio in the dust and a relatively low ratio in the bedrock, and the soil is in between, helping emphasize the idea that these soils are a mix of dust and rock. But the A horizon is generally more similar to the dust than the subsoil, which provides the additional nuance that these soils are being conditioned by dust deposition on the surface. Going a bit farther in that and playing with the fingerprint of the dust versus the soils in the rock here, what I'm plotting are radiogenic isotopes, so the strontium-87-86 ratio and what's called epsilon neodymium, which are two somewhat more sophisticated ways at evaluating immobile elements or immobile constituents that are apparent or present in trace quantities in the minerals that are in the dust and the minerals that are in the soil. And identifying what's unique about these materials. And here we can very clearly see that the dust samples, which plot in this fairly focused cloud up here on the upper left of the diagram, have absolutely nothing to do with the local rock samples, which plot primarily in the lower half or the lower right of the diagram. They're very, very different things. And I don't have a lot of soil data on this plot. But the soil data are the ones plotting right in here. So it's a third time now. Essentially, I've shown you 3 different lines of evidence supporting the conclusion that these soils are arrayed along a spectrum between a pure dust end member and a pure rock end member. They're a mixture, but they happen to be dominated more by dust than by rock. And I could take those data there and present them in a different way in a mixing model form, and essentially look at 100% rock versus 100% dust on the other end, epsilon neodymium on the right axis, the strontium 87-86 ratio on the left axis, 4 soil samples plotting on either end, or 4 samples plotting on either end, and the mixing models as the lines in between. The intersection of these leads to the conclusion that the soils in this area, the upper meter of the soils in the high Uintas, are composed of anywhere from 48 to 80% dust by mass, which is a nice way to put a number on what I've now hammered away at for my last several slides. These soils wouldn't be anything like they are now were it not for the deposition of dust over time. To the point that 80% perhaps of the mass of the soil that's up there might not even be there if it weren't for dust deposition over the long term, which I find just remarkable. And when you consider the differences in the properties between the dust and this relatively mineralogically simple quartzite bedrock, it goes a long way toward explaining why these environments are functioning the way they do. It's because of the dust deposition over time. What's exciting then is what dust squared afforded in terms of the possibility for expanding this effort. And so in the fall of 2020, at the start of the Big Dust Squared project, I said, well, what I would like to do is evaluate how regionally extrapolatable these interesting conclusions from the Uintas really are. And I'm going to do that in part by greatly expanding the network of these passive dust samplers. And so this is what the network looks like now. The ones in the Uintas are still in operation, and there's actually one more that I added at the far western end of the range. But maybe more importantly for showing my logic here, there's one in the Wasatch Mountains now, co-located the study site that's managed by one of my Dust Squared collaborators, to help us understand a bit more about dust coming off of the Great Salt Lake Desert. Similarly, there's a collector at the University of Utah, and there's one in Provo at BYU to get at dust even slightly farther to the west and upwind, and to get at dust in a more urbanized setting and to try to tease out the anthropogenic component in that dust chemistry. And from the mountain perspective, I dotted collectors on mountain summits across a really wide region that I just kind of refer to as the outer arc. So down here outside of Moab, high in the La Salle Mountains, in the Tusher Mountains in southwestern Utah, in Great Basin National Park, on Wheeler Peak in the South Snake Range in east central Nevada, at the south end of the Ruby Mountains in northern Nevada, in the Independence Range in extreme northern Nevada, and in the Albion Range in southern Idaho. These sites were partly selected to just create this type of spatial distribution to give me the chance perhaps to intercept dust coming from the west and the southwest before it interacts perhaps with the urbanized areas in northern Utah. Also to see what is going on with dust and soil over different bedrock types. Some of these are locations where the bedrock is quartzite. Others are rock types that we would predict would be more weatherable. And I wanted to see if the role of dust deposition in terms of controlling soil properties varied depending on how easily the bedrock breaks down. I can show you some data from that expanded network. It's a lot more work to go to all those sites. It's a lot more work to process all those samples, but it yields an even richer data set for evaluating and testing hypotheses about what's going on across this wider region. Here from just the first 2 seasons where the full network, or almost the full network in this case, was in place, we can see that spatial and temporal variability in dust flux occurs on an even more dramatic scale when you consider more locations than just the Uintas. So here, for instance, in the winter of 20 to 21, the flux was really high in Salt Lake City, really high at a reasonably high elevation in the Wasatch here, really, really low in the South Snake Range. And we move into the summer when the last couple of collectors were installed. That low value here in Great Basin National Park, that seems to hold. The really, really high value in Salt Lake City seems to hold. So some of that's I could have predicted that Salt Lake, low elevation, close to the city, closer to the lake, might have been dustier, but I don't think I would have predicted that it would be relatively low values at high elevation in Nevada. Similarly, we can see in those radiogenic isotopes that a lot of different source areas are involved in emitting this dust. So here we're once again looking at strontium-87, 86, and epsilon neodymium. The main idea here is that if this, rocks have different fingerprints depending on their individual geologic histories, so different regions would generate dust with different fingerprints. And clearly, the dust is really different in these locations. So the numbers on here are the collector in northern parts of Nevada. The dust 15 collector has absolutely nothing to do with any of the others and is quite a bit different in terms of where it plots compared to all of the Uinta collectors, which fall inside this oval here. I didn't show them all just for simplicity. The colors on here are the seasons. The orange are the winter collections, the blue are the summer collections. And so you can see, perhaps reassuringly, that at some of these locations, there's no real difference in the radiogenic isotope fingerprint of the dust from season to season. 11, they overlap. 6, they overlap. 12, they overlap. But that's not always the case. Dust collector number 13, it's hard to see, but it's plotting there in the winter. It's plotting here in the summer. The lack of overlap implies, or essentially requires, that at least part of the dust landing at that location in a different season was coming from a very different place. The same for number 10 down here and so on, number 9. So interesting variability there. Geochemically, the sites that are closer together spatially tend to be more similar in terms of their chemistry. Again, maybe not surprising, but great to have the data to evaluate this over a larger area. What I'm doing here is I'm plotting, for instance, dust 15 and the correlation coefficient, or the R-squared value, between the geochemistry of the dust there and at all the other sites. And the highest values are in the yellows, kind of light greens, and the lowest values are in the blues, or the dark purpley blues. So dust 15 way over here, geochemically, has a great affinity for the sites on the western part of my network, and the ones farther and farther away tell the opposite story. And if we look at dust 8, which is the far eastern end of the Uintas, we see the flip-flop entirely. That site has a lot to do geochemically with the other dust collectors in the Uintas and very little to do with the dust collectors out here. And I thought dust 9 was interesting. This is the one in the Wasatch. So it's kind of right in the middle. It has a fair amount to do geochemically with the sites to the west and much, much less to do with the sites to the east. So it's almost located on kind of a bifurcation in the middle of this area. It's also a regional boundary between the Great Basin and the Rockies for sure. And the last thing I'll show you, something I've been playing a lot with recently, is trying to figure out, can we explain all of the data that I just showed you in terms of which regions are contributing dust to these particular locations where the dust is being collected. I've been working with Derek Malia at the University of Utah on this in particular, because he has really sophisticated ways to do back trajectory modeling and figure out what land area air masses passed over before they reached a particular location on the landscape. So in my case, one of my dust collectors. So he invested a fair amount of supercomputer time in running back trajectory analyses, not just for single storms or single dust deposition events, but rather for like the entire 9-month period that all of my collectors were deployed and so on. We were really curious, would this just generate like a blob, or would this actually generate patterns with a certain degree of structure in them? So what you're seeing here on the right, I could have labeled this better, but this is the pattern of what parts of the landscape the air masses passed over most frequently on their way to the dust number 1 collector, which I can kind of hover over there. It's in the east central part of the Uintas, and this was for the winter season of 2020 to 21. And you can see the ghostly echo of some familiar topographic features like the Snake River Plain. You can see maybe preferential pathways of dust moving their way up through southwestern Utah, out of southern Nevada and so on. It's really cool to see the output from these. The thing that I did as a first cut at trying to interpret this is I empirically figured out, okay, what's the threshold that I would use to highlight the hot zone, or around each of these collectors, the location in which the air passed most frequently en route to the collecting site. And to be clear, that doesn't mean it picked up dust there, but it means it couldn't have picked up dust from places it didn't pass over. So it's certainly part of the story. And it's very interesting to look at those hot zones or those footprints for the different collectors. Here's just summer of 2021. Almost all the Uinta collectors have exactly the same footprint. That's not too surprising. They're really close together. But the divergence as we move out spatially across the wider network of dust samplers is kind of striking. Like dust 14 down here is sampling the Colorado Plateau in a way that the Uinta collectors just really aren't. Or dust 15 up here, which I showed had the very oddball radiogenic isotope signature. It's sampling a swath of northern Nevada that only barely overlaps with the pattern of the dust contributing landscapes for dust 11. That's nothing to do with the others. It's interesting as an approach for starting to think about where's the dust coming from. And the final piece of that is in the GIS. I took each of these like white polygons here that define the hot zone for each individual collector for each season. And I clipped them through a geologic map to try to figure out, okay, what are the dominant lithologies in those different areas, whether they're dominant rock types or sediment types. And it will surprise no one that they're really different. I think geology is mattering quite a bit here. From left to right across the bottom, we're looking at the summer season. 1 through 8 are all in the Uintas. And so the bar charts here really look pretty similar to one another because the footprints were similar. But things get quite a bit different when you branch out from there. You know, dust 11 in the Ruby Mountains in Nevada, the likely contributing area for much of that dust is 80% blue on this particular plot, is 80% unconsolidated quaternary sediment on old lake basins and alluvial fans and so on. Or dust 14 over here is, you know, mostly a green bar on this plot. It's mostly clastic sedimentary rocks. It's mostly the rocks that we see in the canyonlands and so on, which are uniquely poised to be contributing to that site and so on. So I thought that was a really interesting conclusion. And to pull all this together for you before opening it up for our discussion, I think that this network of collectors initially in the Uintas and the analysis of the mineralogy, the geochemistry, the isotope fingerprints really nicely illustrated the profound role, the profound significance that dust deposition over, given this landscape position over long term, you know, hundreds of thousands of years, I suspect, has had on the formation of soils and that of an environment. And similarly, that dense network of collectors nominally emptied twice a year provided a new perspective on the spatial and temporal variability of dust flux into an alpine environment like that. And now that I have the larger network of collectors as part of the Dust Squared project, continuing the original ones, adding in the new ones, and all of the contributions that my excellent colleagues can make through their modeling expertise, et cetera, it's becoming clearer and clearer to me, at least, that much of the dust in the, you know, the silt size fraction, the material that's actually reaching the ground in these alpine environments and potentially contributing to soil formation and ecological functioning, much of that I think is actually sourced from not all that far away. If it were really broadly uniform material that was a mixture of stuff that had traveled an awful long distance, I would suspect it would be quite a bit more uniform from dust 11 to dust 12 to dust 14 and so on. And instead the material is vastly different, which I think is best explained by the role of the immediately surrounding lowlands as a source for much of this material, at least in the grain sizes that I'm focusing on. So I promised folks I would go like 35 minutes. I think I basically did that. And I really look forward to spending the next 10 minutes or however long we have entertaining your questions and seeing whatever feedback that you might have for me. So thanks so very much for your attention.
Thanks, Jeff. That was fantastic. Do we have any questions? I see some applause in the
Thank you.
Group.
Corrine looks like she has a hand up in the chat.
I do. I have a question, several questions. Thank you.
Okay.
Come on, Jeff. That was so interesting. I have several questions, and I guess you touched about some of them, but maybe there's like there's like several difference. So I think you have this beautiful way of looking at like urban impact, if there's dust that also interact with some pollution. And I'm wondering if you can, or maybe you have done it already, if you can identify long transport dust, like dust that come from Asia, compared to local dust? And then if you can look also on anthropogenic dust in some of your samples.
Yeah, exactly. You know, the design of the expanded collector network is to an extent intended to provide that opportunity. That's the logic, and that's a big part of the overall story of the source to sink approach that the Dust Squared collaborators are employing. I honestly thought I would see more in the way of a uniform signal in the dust samples I was collecting. If you had asked me if I had given this talk 2 years ago and was talking about this in a more predictive manner, I kind of expected I would be developing a story that was more about the similarities between what I'm seeing in these widely scattered sites. And undeniably, there are some, but right now, at least in my current frame of mind and the most recent analysis I've been doing, I'm really struck by how different they are, which is certainly the emphasis I gave you toward the end. Moving forward, I think it's going to be fruitful to not be stuck in one track or the other. I think it'd be really useful, for instance, to dig deeper into the geochemistry and try to pull out, okay, so what are the most similar components of the dust? Can I essentially develop potentially a synthetic impression of what, or description of what the background dust is, something that might be Asian, something that I would suggest is generally farther transported and therefore is better mixed. But right now, I think at least the locations I've selected or the collector types I'm using, that material is subordinate and it is kind of swamped by the magnitude of the material that seems to be more or better explained by coming from like the transition between like local and regional, not immediately local, but not vastly far traveled either.
Thank you.
Thank you.
Okay, our chat's filling up here. A question from Arnold Downey. How does the dust deposition sampler deal with precipitation? Does it depend on evaporation to not overflow, or is there a drain? And if it's a drain, do you not lose dust from the sampler? And great presentation, by the way.
Thank you, Arnold. Great question. I see Meredith Reheis is in attendance here today, and long ago when I started thinking about this, I, like everybody else, turned right to Meredith for advice about how to collect dust and the marble dust trap and its simplicity. How could you adapt something like that for a place that wasn't the Mojave, but rather a place that was actually going to get, a meter precipitation in liquid form over the course of the year? My solution to an extent involves those beads, which I always buy black beads. And the idea is that these things are going to heat up and they're going to try to just blast the water right back out when the sun comes out, the evening after or the day after the big rainstorm or something like that. And then there are drains actually in the collectors at high up on the sides, small diameter trickle drains, essentially. There's no way to know how much I might be losing. On the other hand, I see very little evidence that the collectors ever overflow even. I don't see like a line of pollen or something, which is visibly distinct right up at the elevation of the drain hole, suggesting that they spend a lot of time overflowing. I know from firsthand experience that they're nearly, I wouldn't say they're always dry, but they're quite often dry when I go to them, no matter how wet it's been in the recent past. And the beads are always really warm. I think the simple idea of like a little passive heating actually works reasonably well. Is it perfect? No, nothing is. There's always biases and there's always challenges that are inherent in trying to do this. But I've been happy with how well this design has worked, given the location and the restrictions. I should mention the Forest Service required that they be on the ground. That's why they're not, up on some pole 2 feet off the ground or something. And given the conditions and the wind speeds and the ice loading in the winter, I think having them up off the ground would have caused me all kinds of other problems. So you take what you can get. And I've been happy that they've worked as well as they have.
Thanks. David Huber is wondering what the source and site number for the site in the Snake River Plain is.
Yeah, the source, well, I mean, it's hard to say. The site number, that's my number 16 dust collector in the Albion Range on Harrison Peak, which is another quartzite location. So in part, I was drawn to that. Another place where I would propose the bedrock was not weathering very fast. And I'll also admit that I was intrigued about what I might see being more proximal to the Snake River Plain, different rock types for sure, lots of seasonal surface disturbance from agriculture and so on. So that was one of the most recently installed collectors, as you could gauge from its number. So I'd have slightly less data from that location yet to spin up a grand story, but it's still there. It's still working along with the others. So we'll have more data coming soon.
Meredith is saying, many thanks for expanding to the high country. What about anthropogenic elements like lead and arsenic, etc.?
Yeah, thank you, Meredith. We see a lot of them. I didn't mention that at all, but even in the very first year of collection from my Frodo network of the first 4 collectors in the Uintas, boy, were the abundances of cadmium and lead and copper and bismuth and mining related elements to follow the approach that Rich Reynolds is also here. He showed really clearly that those elements were artificially high in a lot of otherwise pristine lakes in the Uinta Mountains, presumably because of mining activity over the last century. So definitely see that in the dust samples year after year. Interestingly, my colleague Greg Carling, who at BYU, who's working, as I mentioned, on dust and effects on stream water chemistry, he sees that our anthropogenic load of these metals in the dust get carried over into a spike of those metals in the spring snowmelt flood, which is a sign that this is certainly has the potential for some ecological impacts. So that's part of what the project will focus on going forward.
Jason Price is asking, can you say anything about the solubility of primary minerals in the dust? Would weathering of dust significantly contribute to stream solutes at the watershed scale?
Yeah, it's a great question. The basic concern or the question about solubility is something that I've always wondered about, simply because it's relevant to the design of my entire project, right? As I mentioned, I'm collecting dust in these open, passive samplers, and then I rinse the dust out with water and I bring the water back to the lab. Am I losing minerals in that process that might be dissolving? This past year, I finally got smart. Some of you are probably shaking your heads, but I finally got smart and I saved, subsamples of all water, which we'll analyze compared to blanks. And we'll try to figure out, are we actually dissolving something out of the dust samples in the transit time between the collector and the lab? So there's that piece of this. And then exactly how the weatherability is a whole nother story, one of interest, like thinking of the clay minerals in the soils, like how many of these clay minerals are delivered as clay minerals in the dust, and how many of these clay minerals in the soil are delivered as, feldspar or something else that we wouldn't think would weather very fast in this type of environment. But if you give it hundreds of thousands of years, can we still make clay minerals out of that? And in that process, are we still releasing a dissolved load into the surface water that might be serving as a pH buffer and things like that? So this is where, again, I focused on the soil part of this afternoon, since that's my main role in Dust Square, but it's just such a luxury to be working collaboratively with folks like Janice Brainey or Greg, whose expertise is really on the ecological context or the hydrologic context of what's coming from the dust as it weathers. So stay tuned and watch for future talks, perhaps by members of the team, to get better answers for that great question.
Meredith, your second comment, I don't know if it's a question or just a comment, or if you have something you want to add, feel free to just unmute yourself if there was.
It was a comment, but as a follow-on to the fact that Jeff found the most distinct mineralogy in that northern Nevada site, I think that's up in the volcanic terrain. So just a point.
Absolutely. Yeah.
Wayne has a question. Have you or your colleagues looked at microbiome communities and any indication in terms of dust sources?
Another great question. And again, you surround yourself with good people and good things happen. So Zach Onderud at BYU is an expert on exactly that, looking at the dust microbiome, using that as another technique for dust fingerprinting and source identification, as well as what's happening in the soils. And so Zach is leading that effort for Dust Squared, and it's exciting to watch what's coming out of that.
Okay, Stuart Evans is wondering, given the large interannual variability you showed, or have ideas about why some years are dustier than others? Is it extreme weather events, changing land use, different back trajectories?
Yeah, it's probably a whole bunch of things, let's be honest. But something that I'm always struck by is, my collectors, which are on the ground, get buried, at least been somewhat in the snow, and then they have all this dust in them when I come back in the summertime, for instance. Is that wet deposition, dry deposition? I don't know. Is that two really dramatic afternoon dust storms, or is that mostly background dust, which is maybe wouldn't have been that obvious if someone had gone up there and dug a snow pit, but it's actually really, in terms of the total volume and total mass, quite important when you consider the snowpack as a whole. It's really hard to say. I did publish a paper last year that analyzed the 10 years of data from the Uinta collectors, the Dusty Decade paper, as I took to calling it, where I was able to show that there was a statistical correlation between the flux of dust to these collectors in the Uintas and metrics for aridity in the Southwest, which on the one hand is not a surprise. But on the other hand, like aridity metrics have been shown to match with, particulate in the atmosphere, or they might have been shown to match with the dust emission from certain study plots out in arid landscapes. But this was like the first time that a network of collectors on the ground, focused in an alpine setting, could actually demonstrate that, when it's drier in the southwestern US in terms of a drought metric, we actually get, statistically speaking, more dust deposited on the ground, actually reaching the ground in the mountains. But it's messy. And so there's a lot of other variables that are clearly playing a role.
Okay. I don't see any additional questions in the chat. We'll start wrapping up unless somebody has anything they want to ask or add. Just feel free to unmute yourself.
And Jenny, I will just mention, as I should have emphasized earlier, but anyone in this audience who's curious about ways to connect with or interact with or collaborate with or piggyback on our infrastructure, anyone who wants to work with Dust Squared, please feel free to reach out to me. That's a big, the headline of the whole name of NSF's effort here is the Collaborative Critical Zone Network, right? So the more the merrier. So please don't be shy if participating in some way is of interest to you.